Hi everyone, my name is Pranay Manocha and today I'll be presenting our paper NORESQA, a framework for speech quality assessment using non-matching references on behalf of folks at Princeton and Facebook Reality Labs Research. So let's get started. Accurate and reliable assessment of speech quality is critical for a wide range of real-world applications like telephony, voice over IP, and hearing aids. The gold standard for SQA is the evaluation by humans. However, these subjective evaluations are not scalable and can be time consuming and costly, as they often need to be repeated multiple times for each recording. Therefore, automated objective quality metrics are much more practical. Traditional objective metrics like PESC are automatic and interpretable. Unfortunately, they can be unstable even for small perturbations since they rely on complex, handcrafted rule based systems. These methods also need the exact paired matching reference for comparison. Moreover, these are non differentiable and cannot be leveraged as a loss function for downstream deep learning tasks. Recent research in SQA has focused on learning speech quality directly from data, either by creating differentiable proxies of objective metrics like PESC or by training directly on human judgments, for example, DPAM and CDPAM. These methods can be grouped into two categories: full reference and no reference. Full reference metrics based on neural networks are differentiable and correlate well with human perception, but the requirement of a paired clean reference limits their applicability to real world scenarios where the paired clean reference is not available. On the other hand, no reference metrics are trained to estimate the quality without any given reference. Metrics like DNS MOS that are trained directly on a large dataset of human ratings like mean opinion scores MOS correlate really well with human perception in a constrained setting but fail to generalize across unseen perturbations. Moreover, collecting such a dataset is an uphill task and requires considerable resources like uniformity with respect to hardware and listening environments amongst different raters to ensure consistent ratings, and even then have extremely high variance in the ratings that poses high challenges in training robust models. Lastly, the lack of any reference is itself an inherent challenge of the formulation, since a model is forced to learn a distribution of clean references which is highly subjective and depends on external factors like mood and experience, therefore, making it difficult for the model to be able to generalize to unseen conditions. Therefore, our focus is on creating a framework that is usable in real world settings that doesn't require the same matching reference. Moreover, the dataset should be easy to curate and should have a low variance, therefore, making it easier to train neural network models upon. So, based on these features, we propose our framework NORESQA that stands for Non Matching Reference Based Speech Quality Assessment. It relies on random reference to provide a relative quality score for any given recording. This is inspired by an observation from human perception that we are able to compare recordings with respect to quality, irrespective of the actual speech content, even when the recordings contain different speakers, languages, or even words. Moreover, comparative tests are relatively easier for humans than absolute ratings, and relative scores tend to have a lower variance and have less noise. The framework relies on two non-matched recordings as inputs, which are shown as xi and xj in the given figure. It is passed through a stack of convolutional layers that learns the feature representations and temporal aggregation. To train the network, we follow a multitask and a multi-objective learning setting. So let's have a look at it in some more detail in the coming few slides. The multi-objective learning setting optimizes over the two objectives together. Here, we rely on two signal processing measures, namely signal to noise ratio SNR and scale invariant signal to distortion ratio SISDR, to compare the quality across the two inputs. Both metrics have various desirable properties and are fundamental measures to quantify the quality of signals. They correlate really well with human perception and have been used extensively across various tasks. The multitask learning setting involves solving two tasks together. The first task being that of a preference task, which looks at which audio input is of a better quality, and second is the quantification task, which estimates the quality difference between the two audio inputs. Disentangled learning through two audio or through the two tasks makes it much easier for the model to focus on quality attributes It also makes the model much easier to use in the sense that if only the preference results are needed, or if only the absolute quality differences are needed, the appropriate head can be usefully adjusted. And lastly, it also makes extending the framework to more than two inputs easier. So let's have a look at the training procedure in action. We first select two clean recordings from a clean dataset and then choose two noise recordings from the same dataset or from the same class of noises. For example, any two recordings from the class of bird chirping in this given example. Then we choose any two levels of noise and add them at the respective levels to obtain the noise added recordings, which are then inputs to our framework NORESQA. The output of the preference task is a probability score of which input has better quality. The standard binary cross entropy is used to compute the loss in this case. The output of the quantification task outputs a probability rating over the k classes of outputs where the relative difference lies. This is posed as a classification problem where the space of SNR and SISDR differences are divided into k equal bins. Since standard cross entropy loss doesn't take into account interclass relationships, we use Gaussian smooth labels. For example, the kth class is semantically much more closer to the k plus 1th class than, let's say, the k plus 4th class. And the final loss to the model is LP plus LQ, which is the sum of the two task losses, and this is how the system is trained end to end. And here we show a simple example, but in practice, we select the perturbations from a large set. Our model can predict the quality of a test recording X test with respect to any provided reference X reference as shown by the figure on the right. As mentioned earlier, this reference need not be the matching clean reference. The output of the preference task tells us the sign, whether X test is better or worse than X reference, and the NeurIPS score gives us only the magnitude of difference between X test and X reference. Additionally, the true or absolute quality can be computed by using clean or high quality speech recordings as references. To also reduce variance in the estimate, we can sample multiple references and obtain an average NORESQA score. And as baselines, we use PESC and CDPAM as full reference baseline. CDPAM is a full reference approach trained on a dataset of human pairwise subjective ratings. And being full reference, these methods require the paired matching clean reference for quality assessment. We also use DNS-MOS as a non-intrusive SQA method. It is trained on a large-scale dataset of MOS ratings, and we compare the above models with our NORESQA model that is trained entirely using simulation. We exhaustively evaluate our proposed framework in various ways. First, we objectively check the performance of our framework across tasks and properties. Next, we compute correlations of our metric with existing diverse datasets. And lastly, we show the utility of our model in improving learnability in a downstream task, which is that of speech enhancement. Here, I'll show a few selected results, but please refer to the paper for more analysis. We study robustness with respect to language and gender by using non-matching references across languages and genders. Our test recording is always randomly selected from the English dataset, and our reference recording is randomly selected from any of the multi-language datasets, including Mandarin, French, Arabic, Turkish, Spanish, and a variety of Indian languages, including Bengali, Gujarati, Hindi, and Marathi. The model performs fairly well, which suggests that the model is invariant to language or gender and only considers acoustic differences to assess the relative quality. Next, we check how well our metric correlates across different perceptual subjective datasets in MOS and 2AFC. We consider 10 different datasets spanning across well-known speech problems, including speech synthesis, dereverberation, voice conversion, speech source separation, telephony degradations, bandwidth expansion, and a variety of general degradations. For correlation with MOS ratings, we compute Pearson and Spearman correlations across our metric with the MOS rating from the dataset. And for the 2AFC triplet dataset, we compute percentage accuracy to see how well our model can predict the same judgment as humans. And finally, we also use our non-matching framework in various ways. First is the paired way, in which we obtain the absolute NORESQA using the matching clean reference. Second is the unpaired way, where a clean non matching reference is randomly chosen each time, and as shown earlier, we can get a much more reliable score by averaging across multiple non matching references. In this case, we take 100 references for each test recording. The third case is that of unpaired local fixed, is where the non matching reference dataset is fixed for every dataset separately. And lastly, we have the unpaired global fixed, in which the non matching reference set is fixed globally across all datasets. These tables show the MOS correlations across different datasets. We see that our model is comparative to baseline methods, including full reference methods and DNS MOS, that were trained on large datasets of human judgments. Results also suggest that our metric is a good substitute for full reference methods in several cases, as it stays useful in practical and real world situations where the clean matching reference might not be available. Next, we look at the triplet accuracies where we obtain that the NORESQA outperforms the baseline DNS MOS by a considerable margin, which shows that our metric generalizes not only to MOS but across to different perceptual tests beyond MOS as well. And finally, coming on to ablations, we first verify the advantage of our relative quality difference prediction as compared to the absolute quality prediction model. We observe that our relative quality model outperforms with a considerable margin over the absolute quality prediction model, which shows that learning a model to predict relative quality differences is much better than the absolute ratings. Moreover, we also observe that providing even a non matching clean reference to an absolute quality prediction model also improves the performance over not providing any reference. This highlights the usefulness of two features of a metric. First is by predicting the relative quality scores, and second is by providing non matching references. Next, we verify the importance of our multi objective learning strategy of optimizing over both SNR and SISDR differences. We observe that using either head alone outperforms than using both heads together, which suggests that using a multi objective optimization helps learn a better general representation. And lastly, we also verify the performance of the metric when considering a set of 1, 10, and 100 non matching references. We observe that averaging the scores over a larger set of non matching references reduces the standard deviation in the scores, which leads to much more stable predictions. We also observe that our metric works equally well for scenarios where we take any random set of clean recordings as references, as in the case of fixing a set of references for each dataset. And lastly, we show the utility of our NORESQA model and framework for training a speech enhancement system. We use our framework to first pre-train the speech enhancement model in a way that does not require the exact matched pair of recordings. We show that pre-training the network using NORESQA as a loss function can lead to improvements in performance. After the pre-training stage, the model can be fine-tuned for enhancement following the typical paired learning strategy. And these are models that are trained on one third, two third, and the full training dataset. We see that pre-training consistently outperforms all metrics for all the baseline methods. The improvements coming from the pre-training with NORESQA show the potential of leveraging the differentiable NORESQA across various downstream tasks. And in summary, we presented a new framework for speech quality assessment using non-matching references that addresses the key limitations of no reference metrics. We show that our metric is comparative to existing full reference and no reference baselines. Furthermore, we show that the metric can be directly optimized over as a loss function in the task of speech enhancement using a pre-training strategy that uses a large unlabeled corpus for training the enhancement model. And going forward, our focus will be on developing novel methods under the NORESQA framework, which can correlate better with human subjective ratings. So with this, I'd like to conclude my presentation. Thank you all for listening.